Okay, so the geometric series, I'm going to give you the definition. This is a geometric series has this form. There we go again. Okay, so the index starts at 1, infinity, and A will be a constant, R will be another constant, so you see the index exists in the exponent. So let's see an example, what one might look like. Let's make one up. So in this case, I'll have A is 2, and I'll have my R as a half, and that's to the negative 1. So if I were to expand this just a bit, I'd have 2, the 1 half to the 0, which is 1, 2 1 half to the 1, 2 times 1 half squared, 2 times 1 half cubed, etc. Okay, so one thing, a very important point, is that you have to analyze this as a geometric series, it has to be in this form. The index should start at 1, A needs to stand alone, R needs to have the exponent n minus 1 on top of it. There's not much room for negotiation here. If it's in this form, the analysis is easy. All right, so we're going to say that that the series converges when it's all dependent on this R. The absolute value of R is less than 1. That is between negative 1 and 1. So we just read R and we make this determination. Otherwise, it diverges. So it diverges when absolute R greater or equal to 1. And this is one of the only series where we can actually evaluate what it converges to, should it converge. And that is this nice little simple formula, A over 1 minus R. So we can actually find the sum of a geometric series that converges. So if you were presented, say, with this series, right, it's in the correct form, R is a half, certainly converges, and I could even find out what this sum is. So this will be 2 over 1 minus 1 half. So I have a half on the bottom, bring that up, it's a 4. So again, just keep in mind what that means. Right? That means that when we talk about convergence of a limit, that means that the more of these terms that I add on, I get closer and closer to 4. I'll never reach 4, but I can get as close to 4 as I want by just adding more and more and more and more. Okay, so it's a relatively easy check or analysis. So what kind of problems are you going to see? All right, this is too easy for us. It'd be nice if this is what we had. So some examples of what the real problems will look like, and these will be in the homework. The homework problems will say this. Determine whether the following geometric series converge or diverge. If it converges, what does it converge to? So let me show you what one might look like. Let me find one. And I'm just going to write, I'm not going to write out everything I just said in terms of instructions. I'm just going to write the series down. So this one looks like this. So right away, I see my index is in the right position at 1. Now I have 2 to the 2n, and I have 3 to the 1 minus n. Now when you look at that, you can see right away it's not in the correct form. So what's to make you even think it's a geometric series? Well, the easy answer is that the problem statement indicates that. So the goal is to go from this form into something that looks to be in this form. And this is just done through really pretty easy steps, properties of exponents. So that's stuff that we've been using all through our whole career. It's taught in pre-calc. So you're going to do this in multiple steps, and your steps might not always look like your neighbor's steps or my steps. If you put an equal sign, as long as what comes next is equal, you're okay. But we're going to do some manipulation so that it looks like what it needs to look like to be in the correct form. So I'm going to be real deliberate here. And I'm going to even put what I'm doing. I wouldn't expect you to do this on an exam. But 2 to the 2n, right? This is a product, this 2n. So we can say that that's 2 to the 2 to the n. Right? What's 2 to the 2? That's 4. 4 to the n. So I'm going to replace that with 4 to the n. Is step 1. Okay, a little better maybe. What about 3 to the 1 minus n? Well, you think about if you have division, I'll put 3 to the 1, that's 3. 3 to the 1 over 3 to the n, right? Typically we'd go that way. But we're just using kind of that property kind of in reverse. So I have 4 to the n times 3 over 3 to the n. Okay, now just a little rearranging. I'm going to just, this is multiplied by this. I'm going to just exchange these positions. So it looks like I'm starting to see the a. And I have 4 to the n over 3 to the n. So we have this, right? 4 to the n over 3 to the n is 4 over 3 to the n. And now it's starting to look close. This looks like a candidate to contribute to A. I have this. This is looking like my R. I want to point something out. Notice this has to be to the n minus 1, and I don't have that. This is a very common step in this type of problem, and that is if I have 4/3 to the n, what I'm going to do, I have n of these. What I'm doing is I'm going to break one out, break one off. So if I break one of these 4/3 off, how many are left? One less. Does that make sense? Right, there's n minus 1, there's another one, that gives me n of these. It's a very common step, sort of I call it the breaking a piece off. Okay? Now this is a constant, 4/3, so that'll be absorbed into the 3. 4/3 times 3, that'll be 4. And I now have 4/3 to the n minus 1. This is now in the correct form. 4/3 is greater than 1, so this series diverges. And I want to make this point. When you do the problems in this chapter, I shouldn't have done that. We're going to determine behavior, but we also need to be explicit stating why. Okay, we know why, and I put that it diverges. But I have to tell the reader why. And I'm going to say that this is a geometric series, and I'm abbreviating, with r greater than 1. This is not necessary. That justifies the argument. Okay, so in any of the problems really in this chapter, we're going to end with this, right? This is the behavior, but we need a statement of why. Remember that for all of the problems, and I'll be sure to do that as well. Let's see another one. Okay, let me pick one out of the book. Well, let's see what we got. I want to do one that converges. All right, let's try this one. See what this one does. -3 to the n minus 1, that looks solid, right? Over 4 to the n. This one actually I think will be kind of easy. I hate saying that, but again, this is okay. I got 4 to the n, I want n minus 1. So again, I'm going to break one out. And this is actually quite a simple one. So if I break a 4 out of the bottom, keep in mind that's a fourth. That's in the bottom. And I'll have negative 3 to the n minus 1 over 4 to the n minus 1. So we have this, and this is ready. And I can see that the R value, the absolute value is 3/4. That is less than 1. So I'm going to say that this converges because it's a geometric series, absolute R less than 1. And you would be asked to determine the sum. Given that it converges, what does it converge to? Keep in mind that value is A over 1 minus R. So I'm going to say that this is A over 1 minus R, keeping in mind R is negative, 3/4. So I have 1/4 over 7/4. And if I flip this, I have 1/7. Okay, and I don't think there's anything really overly difficult. No, this was pretty simple. This was a little more involved. I don't think they get much more complicated than the first one. Maybe I should have reversed the order. But just keep in mind the definition of the geometric series, right? It's very important to be in this exact structure. And if you're wondering why, one of the main reasons is if you sort of get halfway there, maybe you can identify the R, but if it's not in the correct format, you're very likely to have the wrong A, which means you're going to have the wrong sum. Okay? So work through those. There's sort of, I think students kind of like these problems. They're not too bad. And next we'll go divergence test.